for design resiliency. Then the next is resilience strategies for integration services. So I have jotted down all services I can think of and what patterns can be used or options we have. For Azure Logic Apps, we can use retries, exception, scopes, DLQ, run history, durable state. With Azure Functions, similar way, retry policies, circuit breakers, queue triggers, async patterns. Event grid, we can use event delivery retry, dead letter destination, geo redundancy, Azure Data Factory, retry, failover pipelines, checkpointing, error outputs. So similar way, you can go through the various options are there. I'm not going to read all of them. The last one is important one, APIM. You can have circuit breaker, retry after policies, caching, throttling. So we have various options there and various patterns we can use. Let's move on to the next one. Now the question is how to test resiliency. So building for resiliency is only half the job because we have done that. But if we haven't tested it, and it means we haven't proven that our resiliency works. So we have to define our failure scenarios. So define what we are going to test. Starting by listing the failure scenarios, we want to simulate transient API errors like queue backlogs, regional outages, or deployment rollbacks. For each one, we have to define measurable matrices like RTO, RPO, MTTR, and SLA. So that sort of stuff, we have to specify those things. So we can't verify resilience if we don't have the success, how success looks like. So we need to know what success is. Um, then we have the second one is simulate outages and dependency failures. So we have to either manually or through automation, we have to turn off dependencies. For example, disable a function app, throttle in API, APIM, or pause a downstream services. Watch how logic apps and service bus or data factory, for example, respond. So do the retry or then queue messages or what happens. So we need to know exactly what happens if we disable any system, any dependency. Validate retries, DLQ, and fallback paths. So we similar way we have to check then when we disable, does it logs message into dead letter queue or message gets lost. So we need to think about those things. Perform chaos testing. I already talked about a little bit. Chaos testing. Introduce random, unpredictable failures like latency spikes or drop connection, throttling, and even you can use Azure Chaos Studio or manual stress scripts to simulate these scenarios. The goal is to observe how your integration behaves under real world turbulence, the challenges, not just an ideal condition. So we have to, basically create a strategy and test all these things and conduct. Another one is conduct load and stress testing. So you can do these things from there are various services which can help software can help us to test our APIs, Azure functions, or any of these things. Then we have test recovery automation and alerts. So in this scenario, we can force a DLQ overflow or an API outage and see if the alert fires or your auto recovery process kicks in. So if application insights or Azure Monitor doesn't alert you within minutes, um, you are blind in production. So we have to test all of them very carefully. Uh, then we have another one is review logs and matrices and observability. So after every test, inspect telemetry in Application Insight, Log Analytics, and Service Bus Explorer. Check correlation ID across components. We have to use KQL and just see that we have correlation ID or trace uh, parent information uh, across all the systems. We, trace parent is more useful when we have downstream multiple systems connecting to so one service. So need to make sure that we have information about correlation ID and trace parent. Um, or even trace state as well if needed. Uh, so we need to make sure that we have those information by firing KQL. Then next is continuously refine and retest. So it's a iterative process. It's not just one time. So we have to schedule and test that everything we have we have designed is working. Now in reliability, we quickly talked about reliability as well. Basically, reliability is the test of resilience. So we there are various patterns we can use to make a system more reliable. Means basically what we're saying is what we discussed in resilience and reliability is the practical uh, you know kind of thing. So we are saying system is reliable, uh, and it will work. It will be business will continue working even systems are down, or gracefully back off whatever happens. In the reliability patterns, we have bulkhead, cache aside, circuit breaker, claim check, compensating transaction saga, compensating consumers, event sourcing, gateway aggregation, gateway offloading, and gateway routing, health endpoint monitoring, pipe and filters, priority queue, publishers and subscribers, queue-based load leveling, rate limiting, throttling, retry, scheduler, agent supervisor, strangler fix. So I will cover a couple of them. I will not go with I will not go every one of them. So I'll cover a few of them so I can just quickly walk through. So bulkhead is very simple. The bulkhead pattern is a type of application design that is tolerant for failure. We're going to read this definition. In bulkhead architecture, also known as a cell-based architecture, elements of an application are isolated into pools so that if one fails, others will continue to function. So what we are saying is that we know that one of the component can fail. We can isolate that component. If it fails, it's not going to affect the rest of the system. And it's named after a sectioned partition bulkheads of a ship's hull. If the hull of the ship is compromised, only the damaged section fills with water, which prevent the ship from sinking. So anyway, so that's the definition of bulkhead. I took this definition from Microsoft website, so it's not mine. Now, if you look at the example which I'm trying to depict here in the bulkhead problem is like in this scenario we have mobile and web application calling APIM, and APIM has only one product and it's a sharing limit and it has shared policy. It's called the logic app. One runtime hosting all flows. Basically, if it's insurance application, claims, renewals, agent sync, all coming through same logic app, and it goes into service bus. It's in the same namespace, but it has a three different queues. Claims, renewal, agent sync, and we it calls Azure function, and that Azure function is the same one app. Now, in this scenario, we can have a trouble, if we have a spike in number of claims, and that blocks other threads in, for example, in logic app, it will block all other as well. Means renewal and agent sync will be deprived. Uh, so we have to think about how to fix this thing. To fix this thing is very simple. What we have to do is we separate. You can use one product for each. No shared limits, no shared policies, and we can use also circuit breaker in APIM. And in the case of runtime, we can have separate runtime for each one. What I'm saying is we have separate logic apps for each of them, and it depends on the amount. It's not like a rule, but we have to see the workload. If it's a very high, we can separate it. If it's not very high, and two are, for example, renewal and agent sync are not very high, we can combine together, then we can have claims separately. And similar way, we have a separate namespace for service bus and queue, and similar way for Azure function. So that is called bulkhead. Let's move on. Cache aside pattern. This pattern loads data on demand into cache from data store. use this pattern to improve performance and help maintain consistency between data in a cache and data in an underlying data store. So it is very simple that it is very helpful in reliability. So um, if we have if we are using cache and we are storing, for example, we have customer data, master data, and we store that data in cache, Azure Redis cache, and some reasons the database is not available, the master data is not available, the system can access, for example, APM is doing that, so system can access the data from the Redis cache. So it doesn't have, if system is down, database is down, still the system will work because we have data in cache. It's a very simple one. You can look at the website as well. It's not a very difficult. So this is interesting one. The circuit breaker is normally it is used in AFM, but can be used in Azure function as well. And the circuit the circuit breaker pattern helps handle faults that might take varying amounts of time to recover from when an application connects to a remote service or a resource. A circuit breaker temporarily blocks access to a faulty service after it detects failures. This action prevents repeated unsuccessful attempts so that the system can recover effectively. This pattern can improve the stability and resiliency of an application. Let's take an example here. So let's say we have SaaS system, and we have a client is um, calling a APIM, and there's no CB, and it's a standard retry. So retry keep on hammering. I have seen these kind of things happening many times in my experience in existing systems, and even people even implemented cloud system. They just relied on retry, and you know after some time retry is not successful, then we need to have a circuit breaker to deal with the situation. So we can have circuit breaker like this. So APIM, a circuit breaker stops the storm at edge APIM in the caller function. We count failures. Once a threshold is hit, we open the breaker. Either first fail with a clean message or degrade gracefully and queue the request or a server or serve cached data. After a cooldown, we probe the backend. If it's healthy, we close the breaker and resume. This protects the vendor API and preserves our capacity and keeps the business running with controlled degradation. Now, in this scenario, we can have circuit in APIM, or we can use in Azure function as well, and we'll log all the information in our system. So you can just read through this, and yeah, we can apply circuit breaker in our APIM to basically protect our downstream system if they are down. It's not going to call again and again, so we can protect.